I put up two transparencies just to remind you what my definition of a lattice is, for those of you who weren't there last Wednesday. What I did last Wednesday, apart from giving some basic definitions, is that I also attempted to motivate you towards what I'm doing today by formulating and illustrating the two fundamental problems that you encounter in lattices, the homogeneous approximation problem and the inhomogeneous approximation problem. And today we are going to see that both of these problems can to a certain extent be solved by means of what is called a lattice basis reduction algorithm. So let's just get started working here and give some more or less obvious definitions. First of all, a sublattice. If I have a lattice, then any subgroup is also a lattice. If you look, for example, at this definition or any other, also the other one that I just took away, if you restrict this map Q, defining the lattice structure, to a subgroup, then again, all of the conditions are satisfied. What I wrote down also here is a term that I borrowed from abelian group theory. I will mostly be interested in sublattices that are pure and that can be phrased by saying, well, I give a number of definitions. You can phrase it by saying that L has a basis that contains a basis for K. What you want to avoid, for example, is that you have an element of L that is not in K, but twice the element is in K. That is the sort of thing that you don't want for a pure lattice, for a pure sublattice. It is a relative notion. It is not just a property of K, it is a property of the inclusion. And the reason that we want to have pure sublattices is that we want to look at quotient lattices too. If we take a pure sublattice of a lattice and we divide it out, then we get something, a finite abelian group, a finitely generated abelian group that again satisfies the conditions of a lattice if I provide it with a suitable structure. What I do is that I look at the orthogonal complement of the subvector space spanned by K. I project L onto that orthogonal complement. The kernel is exactly K. That is because of the purity. The purity can be phrased by saying that K is exactly the intersection of the lattice with its own R-linear span. And then the orthogonal complement is a Euclidean vector space. It is a subspace of a Euclidean vector space. And L over K, as it turns out, becomes discrete in there. So if I illustrate that by means of a picture, here I have a lattice, L, there's a 0. Here I take, you can, for example, take this particular point, you look at the line it generates, and you intersect it with the lattice. That gives you the lattice K. Then the orthogonal complement is the other line. You see that it need not meet any lattice points except a 0. And then when you project all the lattice elements onto this orthogonal complement, then all of K disappears, and all the other cosets of K, all these parallel lines, give rise to points that are discretely distributed in this orthogonal complement. Okay, so that is the lattice structure on L modulo K. If you want to express what the length is of a coset, if I take a coset x bar modulo K, and you want to know what its, so you take, for example, x, so its coset corresponds to this projection, then the square length of this x bar is just the distance of x squared to the subvector space that you are dividing out. All very straightforward and intuitive. What I didn't write down here is that once you have K and L modulo K, then their ranks, as I defined them last time, add up to the rank of L. In this particular case, that comes down to the identity 1 plus 1 is equal to 2. What is also true is that the determinants as I defined them last time multiply. If you multiply this length, which is the determinant of k, with this length, which is the determinant of L modulo k, you get the area of this parallelogram, which is the determinant of L. So that is also a straightforward property. Okay, and now I come to my central notion, and that is a notion of a flag. In fact, flags are so central to my discussion today that actually one might say that I'm not talking about lattice basis reduction algorithms. I'm talking about flag reduction algorithms. And what is a flag? Well, that is a chain of sublattices. I want all of them to be pure. I want them to be contained in one another, and I want the ith one to have rank I. So, for example, if n is equal to 2, there is no choice for f0, that is just a 0. There really should be curly brackets around my 0, but they are never written by anybody, so f0 is just the sublattice of rank 0, determinant 1. L is f2, and the only choice you have is a choice for f1, and you might take this very same k. The condition is that it should be pure. And the reason that this is called a flag is that, well, if you look at the flag, it has a knob, which is a zero-dimensional thing. Through the knob, you have the flagpole, which is one-dimensional, and then you have the actual fabric, which is a plane passing through the flagpole, which is two-dimensional, and this is all happening in our three-dimensional space, which is the F3. Okay. As I just mentioned, rather than talking about basis reduction algorithms, I will talk about flag reduction algorithms. There is a close connection between flags and bases. If I have a basis of my lattice, then I get a flag out of it by simply looking at the sublattices spanned by the first so many basis vectors. So fi is just spanned by the first I basis vectors. It is clear that in that situation you get a flag. And it is also a very straightforward exercise to show that every flag is obtained in this manner. If you look at the successive quotients of the f's, then each of those successive quotients is a lattice, because I'm dividing out by a pure sublattice. The rank is 1, and a lattice of rank 1 is generated by a single element. If I lift that element to fi, then you see that I get a basis with the property that flag is given by the basis. Also, this makes it clear that this basis is not uniquely determined by the flag. If you are given a basis, then there are two types of ways of changing the basis that do not change the flag. First of all, I can change the signs of these basis vectors, relatively innocuous. And the second thing that you can do is that you can add to any basis vector an integer linear combination of earlier basis vectors. And that won't change the flag either. And that is the only freedom. You have combinations of these two transformations. You also have to keep in mind here that the numbering of the basis is very important. It is not just a set of elements, it is an ordered set of elements. Okay, well, in my flag reduction algorithm, I am going to do computations with flags. So if you really want your computer to do those for you, you have to specify a flag. You have to numerically explain to your computer, or the computer has to explain to itself which flag it is talking about, and you do that by specifying a corresponding basis. And we know, I explained that last time, that you have several options of specifying lattice elements. So that is what I am saying here. I should also mention, although it doesn't play a major role in this lecture, that the ambiguity that you have in the choice of the basis elements for a given flag is often used in order to normalize these basis elements a little bit. And that is what I explain here. So for each basis element Bi, you have something that is known as the Gram-Schmidt orthogonalization of Bi star. So maybe I should just go to this picture and look what happens here. For this particular flag, where F1 is my K, I can take my first basis element to be this vector, for example, that is a basis element of K. And for B2, I should take an element in L that maps to a basis element in the projected lattice. So, for example, you can take that element. Or you can take that element. You can also change the sign and go to those. But if you stick to this line, then the wise thing to do in many circumstances is pick a short one. For example, that particular one. And that is what I am doing here. So what you like to be the case is that if you look at this B2, you project it, that is the B2 star, that the difference between the B2 and the B2 star is sort of small, viewed as an element in this subspace. And what you mean by sort of small is defined in terms of the earlier Bj stars. You want to sit in this rectangular box. All these Bj stars are pairwise orthogonal with coefficients ranging from -1/2 to 1/2. And there are several reasons that you might wish to specify the Bj's in this manner, which makes them almost unique, almost, that is to say, up to the boundaries of that interval. If I would have made it half open, it would be totally unique, apart from the choice of the signs. There are several reasons to wish to do this. One is maybe just that you like things to be unique in general. Another is that in the course of these basis reduction algorithms, well, you have to estimate the size of the numbers that you are encountering, otherwise your algorithm may not be polynomial time, and then it may be wise every now and then to change your basis so that the vectors are not running away. So then you perform an algorithm that changes a basis into a basis satisfying this property, defining the same flag. And there are also certain applications, actually not too many, but they exist, for which you are not just interested in the flag, but you are interested in the basis elements. And for the purposes of the application, it is good to make sure that the basis elements themselves are short. And then this is also the proper way, one proper way of establishing this. Okay, so that is what I had to say about the relation between bases and flags. Okay, so a flag reduction algorithm, what is it going to do for us? Well, it is going to look for a particularly good flag. And what is a good flag? Well, intuitively speaking, that is one that has a small size. And the size of a flag is defined to be the product of the determinants of the lattices occurring in that flag. So maybe if I put up this example again, the determinant of 0 and L, they never change. So in the case of a two-dimensional lattice, the size of a flag is just proportional to the size of the determinant of F1. But in general, it will be a combination. And what we want, roughly speaking, but I'm going to elaborate upon this, is find a flag of a small size. And actually, there is a smallest one because there is a perfectly elementary theorem of which I may leave the proof as an exercise, that the number of flags of bounded size for a given lattice is always finite. So in particular, there will be a smallest one. We may not be able to find the smallest one, but we can try. It is similar to finding the shortest vector. We just do the best we can. Now, before telling you how to find a good flag, let me try and convince you that good flags are useful for solving the two problems that I formulated last time. And it turns out that in order to explain this, it is useful to introduce a notion that is a little bit more informative than these, let me keep up that example, than just the size, and that is what I call the successive distances of a flag. So what are the successive distances? Well, in this picture, the first successive distance is simply the length of the first basis vector. The second successive distance is the distance from the second basis vector to the space spanned by the first. So that is the length of this little line segment that I've drawn over there. And in general, the ith successive distance is just the determinant of this rank 1 lattice, fi modulo fi minus 1. So one way of expressing this is by taking a basis corresponding to your flag, pass from the basis to its Gram-Schmidt orthogonalization. So bi star is the component of bi orthogonal to the space that is spanned by the earlier b's, and then you take off that bi star, which in my picture is the projection of that point on that orthogonal complement, you simply take the length. That is another way of saying the same thing. I told you how to compute the determinant of a lattice from the determinant of a sublattice and the quotient lattice, namely multiply them. If you apply that by induction, then you will see that if you multiply all of the successive lengths, you get the determinant of the lattice. And in the same way, you can compute the determinant of each of the lattices occurring in your flag, because they are also built up from these quotients by multiplying. If you express each of the dfi in terms of the li, and then you take the product, then you see that the sf is a product of successive lengths, where the first one is taken n times, the second one is taken n minus 1 times, and in that way it goes down. The last one is taken only once. And this is the number that we want to make as small as we can get it. And you see that if you have a sequence of numbers of which the product is given, your L is fixed, and you want this weighted product to be small, well, you have the largest weights in the beginning. So you want the earlier members, the small, the LIs with I small, you want it to be small, and the later ones, you allow them to be large. That is the only way to make the product small. So what we ideally would like to achieve is to make sure that my successive distances are increasing, or at least non-decreasing, as a function of I. I would love to have a lattice for which the L1 is the smallest of all of them, L2 would be the next, and in that way each next one is at least a preceding one. But it is a sad fact that not every lattice has a flag with that property, but we can see how close we can get to this desired situation. So what we like to have is a sequence that doesn't decrease at all, but what we have to settle for is a sequence that doesn't decrease too steeply. And why is that useful? Well, because, for example, if I have such a flag, then it helps me solve, for one thing, the homogeneous approximation problem that I formulated last time, and maybe I can even find, no, I don't have the formulation here, but the homogeneous approximation problem is the problem of finding a non-zero vector in a given lattice of smallest possible length. So what do we have here? Well, here we have a parameter c, which is at least 1, that measures how well we are doing with making this sequence not decrease too steeply. We would love to take c equal 1, and then it is just a non-decreasing sequence, but we may have to settle for a c that is a little larger. We are going to see later how large we have to allow it to be. But suppose that we fix c for the moment. It somehow can be seen as a measure for the quality of my flag, if you have this C, then this theorem expresses that if I take a basis vector of the very first lattice in my flag, so F1 is the rank 1 lattice belonging to my flag, then first of all, the squared length of that element is, qualitatively speaking, of a similar length as what Minkowski tells me. I gave you Minkowski's theorem on Wednesday, and I told you that every lattice has a non-zero element for which the Q was at most this very same expression, but not multiplied by this exponential function, but just multiplied by n, the rank itself. And that is simply something that nobody knows how to achieve with good algorithms, so that is what we have to pay for. We get an exponential function. It is not too bad, and it seems that it is not too harmful for any application, but that is a little worse than we would really like it to be. So this is almost as good as what Minkowski predicts to exist, especially when n is fixed, of course. In addition, not only is it good in the sense of almost achieving Minkowski, it is also good in another sense. It may be that your lattice actually does much better than Minkowski. And what I am saying here is that not only is B1 sort of short in an absolute sense, or when you average over all lattices in a sense, but it is also short in the sense that if X has another vector that is also short, then this B1 will be not too much longer. So it is a fair approximation to the very shortest vector, the very shortest non-zero vector, which you may have no control over and which you may never be able to find. So this B1 is supposed to be good enough for our purposes. Okay, so this theorem can be formulated by saying that these flags for which these successive distances don't decrease too steeply help us in solving, or at least finding a reasonable solution to the homogeneous approximation problem. The proof of this theorem, let me just show it to you because it is perfectly straightforward. QB1, that is the square length of the first basis vector, that is what I say here, that's the square length of the first successive distance. And that L1 is at most the Li, apart from this constant that we have to allow, we have to apply this inequality I minus 1 times to climb up from index 1 to index I. And now if we multiply this out over all I get the nth power of QB1. I get here c to the power triangular number. And here I get the product of the LIF squared, which is the DL square. And if you look at this inequality and you take the nth root, you get exactly the inequality over here. So that is the proof of the first statement. For the second statement, take any x. This x is non-zero, so that means that it does not belong to the F0, F0 being just a zero lattice. So you look at the first of the Fi's in which it does appear. So you take x sitting in Fi, but not sitting in Fi minus 1. So then you will see that the length square of this x will have to be at least this square of the ith successive distance. Because if you look at how Fi minus 1 is sitting in Fi, well, then Fi minus 1 is sitting in this hyperplane as I sketched. Then the next element in Fi is at distance the LIF, that is where the Bi star is sitting. The next is sitting at double the distance, and that way it goes. So as soon as your x is not sitting in Fi minus 1, it has to pay at least this LIF in terms of its distance to the plane, to the subspace generated by Fi minus 1, and that is, of course, a lower bound for its own length as well. So that is a lower bound that you have for every non-zero x. There will be some I such that this inequality is valid. So now you do the very same thing. You replace the I by 1. You have to pay for this power of c. the I is at most n, and the L1F square is equal to my QB1. And you see that indeed my QB1 is at most the inverse of that number times QX, exactly what I am claiming here. Okay, so that should convince you that these lattices are useful. Now, one thing that I do not want to prove in detail is the second statement on this transparency. I just argued and proved that these lattices, these good flags, good in the sense that the sequence of successive distances doesn't decrease too steeply, gives me a reasonable solution to the homogeneous approximation problem. I claim that it also gives me a reasonable solution to the inhomogeneous approximation problem. Here you have the inhomogeneous approximation problem again from last time. So that is a problem that consists of rounding a given element of the underlying vector space to a nearest lattice element. And I am, in the theorem that I formulate about this, which looks a little technical, restricting to the case that the underlying vector space has the same dimension, because if it doesn't have the same dimension as the lattice, then the first thing that you do is that you project your given X to the subspace generated by L, and you replace the E by that subspace, and the problem will be entirely equivalent. If you have already a certain distance to the space generated by L, there's just nothing you can do about that, so then you have to project. So here is then the theorem. The condition on the flag is exactly the same one. So I have this parameter C. Yeah, maybe before I take it away, it is instructive to look what happens in the ideal situation when C is equal to 1. In that case, QB1 is really the shortest non-zero vector. That is not quite going to be analogously true in the inhomogeneous situation. So here, I take a similar flag. I take an element X in E. Then the statement is that I can find a lattice vector for which X minus Y is sort of small. And what do I mean by sort of small? Well, it is again sitting in this rectangular box that I showed before, except that I had a different type of bracket there, spanned by those Gram-Schmidt orthogonalizations. And then you can give an estimate for how large it is going to be. You can simply take the square lengths of the BI, divide them by 4, and add them up. So that is, again, an estimate in terms, if you like, of those successive distances. But what is interesting about it is that this Y is not just some reasonable approximation to the X. It is almost the best one. Any other lattice vector is at least as far away from X as Y is, apart from some constant that depends, again, on C. So if you take, again, as I did earlier, C equal 1, well, then you have to actually work this out before you compute it. For C equal 1, this number is taken to be n. So if n is greater than 1, you are not doing the optimal thing, but only up to a factor n, so that is perfectly reasonable. Okay, so this is a perfectly straightforward exercise, but I don't want to give the proof. Okay, so what we want is a flag satisfying that type of condition for as small a C as we can achieve. So that is the next issue that I want to address. How good is the best flag, and how do we find maybe not the best one, but at least a reasonably good one? Now, here is a theorem which is maybe interesting, but not quite what I want. I told you before that a small size is indicative for a good flag, but that is not the only thing there is. But this theorem at least gives you an upper bound for the smallest size of a flag of a lattice. And you may think about this, the way you prove this theorem is simply that you start from your lattice, you take a shortest non-zero vector that generates a sublattice of rank 1. you mod it out, and you keep going. You create a flag. You apply Minkowski in each stage, and if you don't make an error, and if I did not make an error either, then that is the expression that you get. This is, again, an exponent that is necessary. You can figure out this exponent before you do anything just by looking what happens when you scale L by a certain constant. Then dl will catch the nth power of that constant, and the flag will catch a triangular number power of that constant. So that is the quotient of that triangular number by n. But that is not really what I want. The way I want to measure the quality of a flag is not just by means of its size, but it is by means of the C that it achieves. So the question is, what is the best C that we can achieve? And, well, that depends on the lattice, clearly, but there is a theorem that any lattice has a flag for which C equal 4/3 is achieved. And 4/3 is best possible in the sense that if you replace it by a smaller number, then I can write down a lattice for which it is not true. You can write down a lattice of any fixed rank as soon as the rank is at least 2. So that is something that you may also want to think about. Now, this theorem is important for us because other than Minkowski's theorem, its proof is perfectly constructive. And the construction underlying the proof, that is almost the same as the LLL algorithm, the lattice basis reduction algorithm. So let me go over the proof of this theorem, which is really the heart of the lattice basis reduction algorithm. So what I claim here is the following. I actually claim, if we just stay away from the constructive aspect, just to prove this theorem, the claim is that if you take f with the size smallest possible, then this will be true. And why is that? Well, that is because we believe this lemma. We are going to prove the lemma, so we'll have to believe it. Namely, suppose that the inequality is not true. If this is not true for all I, then there will be a counterexample, so then there will be a j for which it is wrong, for which you have the opposite inequality sign, and then I take the constant to the other side, and I have this. If the thing is wrong, I can find a flag of a smaller size. So if I had started from the smallest flag, that cannot be true, and then the theorem is proved. So that convincingly shows that in order to prove the theorem, it suffices to prove the lemma. And the lemma has a proof that is completely constructive. So how do I prove the lemma? Well, it turns out that in order to construct this flag f prime of a smaller size, it suffices to make really a tiny change to my given flag. I just leave all the sublattices constituting the flags alone, except for the jth one, where j is the index for which my inequality is not satisfied. So that means that f0 up to fj minus 1 will remain the same, and fj plus 1 up to fn will remain the same. So if you think about this, then the only thing that is happening between fj plus 1 and fj minus 1. And that implies that we may as well reduce the entire problem to everything that is happening in between those lattices, which is the quotient lattice, fj plus 1 modulo fj minus 1, which is a lattice of rank 2, this being the difference of j plus 1 and j minus 1. And that is very convenient because two-dimensional lattices are exactly those that I can draw. So this picture, which you have seen several times by now, is now not just an example anymore. It's the only case we need to consider. So how do I go about it? Well, if my rank is 2, then my j is clearly equal to 1, the only lattice that I can change. So I have to tell you how to change fj into an fj prime, and as a result, make the size smaller. In other words, make the determinant of that sublattice smaller. So here is my f1. What I know is an inequality between the L1, which is this length, and the L2, which is the other length. And what I do now is that I pick my second basis vector, not to be just any of those elements. I really pick that one. That is to say, I pick it in such a way that the projection onto this RF1 lies between -0.5 and +0.5 times that basis vector. You can clearly always do that. That is just a matter of rounding reals to integers. So then what do we know? Well, we know that the second successive distance squared is less than 3/4 times the first square. So in that picture, that means that the squared length of this perpendicular line is less than 3/4 of the square of that length. So if I want to estimate the length of that vector, the B2, then its length square will be that square plus that square. This one is less than 3/4 times the whole thing. That one is less than 1/4 times the whole thing, because 1/4 is the square of a half. I'm squaring the lengths. So the total length of this vector is less than the length of that one, because 3/4 plus 1/4 is equal to 1. That is why it is 3/4 in this theorem, and 4/3 if you formulate it like this. So what we do now is that we take this sublattice spanned by B1, we replace it by the sublattice spanned by B2. The length of B2, as I just argued, is smaller than the length of B1, and my F1 prime is now spanned by that second vector. So that is all there is to the proof of this lemma. Now, since this is really the core of the LLL algorithm, I would like to go over this argument once again, but with a slight change. Namely, suppose that we are not really going for this best possible C, but we allow this 4/3 to be a little larger. Maybe we say, well, 1.5 will also be fine, or 2, or 10. Anything that is really larger than 4/3. Then you might see how that affects our argument. If I replace 4/3 by something larger, then in my lemma, my 3/4 will be replaced by something smaller. Maybe, let's say, 1/2, if you start from 2. And how does that affect what I'm doing here? Well, then the square of this length is at most 1/2 of the square of that length. And then I have to add 1/4, so that gives me 3/4. So that is to say that this length is not just less than the other length, it is less by a factor that is at least, or at most, the square root of 3/4. So in other words, in that situation, I can assert a little more. I cannot just assert it is smaller, I can assert that it's smaller by some definite factor, 90% or something. A definite factor strictly less than 1. That is going to be useful later. Okay, now you have seen already really a whole class of algorithms now, all of which might be called the LLL algorithm, modulo some slight adaptations. Namely, the algorithm is simply the following. You want to have a lattice satisfying, you are given a lattice, you want to have a flag satisfying this condition. either with 4/3 or maybe with a larger constant. Let's just not talk about that for the moment. Then what do? Well, you start from any flag. After all, as I told you last time, lattices are supposed to be given by a basis, and every basis gives me a flag. So at the beginning, there is already a flag. Then I simply check whether my flag satisfies the inequality. If so, I'm home. If not, I find a j for which the thing is wrong. I perform this construction, I find a better flag, and I keep going. So that is a whole class of algorithms. I say it is a class of algorithms because I am not specifying which j to choose. I'm not telling you, well, take the first j that you don't like, or take the largest j for which the inequality is not satisfied, or take the j for which the quotient is as small as possible. That is your own strategy, and I would almost say that is an implementation detail. But what I'm going to say about the analysis of LLL will apply to this entire class. Of course, it may be that you can say something better about specific members in this class where you do prescribe how you pick your J.
You say here on the 4/3 is wrong, but are there families of lattices what one can do better?
There are certainly families of lattices that do have better flags. You may have, I mean, your lattice may be an orthogonal sum of several scaled copies of Z, and then there will be a flag for which this is true without a 4/3. But I'm not saying that you're going to find it. We find something that is good, it may not be the best thing that we find. Okay, so now the main thing that you have to consider when you want to analyze the efficiency of this class of algorithms is how many steps does one need to take before you get stuck. Starting from a flag, how many steps can you take before you reach a flag for which the condition in my theorem is satisfied? So one attractive way of formulating this is by means of what I call the reduction graph. So this reduction graph, that is just a graph, usually a graph with an infinite number of vertices, a directed graph. The vertices are the flags, and you hop from flag to flag along the arcs of the graph. And the arcs of the graph, well, those are basically just going from F to F prime, if that is what the proof of this lemma tells you to do. So the formal definition I wrote down here. I allow myself to go in one step from a flag F to a flag F prime. If you can find a J for which the only change that you are making is the jth one, so all the others are left alone. The jth one you replace by something that together with the other jth one is spanning the next one, so that just expresses in this picture that my given basis vector for the F1 and the basis vector I replaced it by together span my two-dimensional lattice. That is this condition. I also want that given those two conditions, I'm really doing the best I can. That just means that in this picture, I am not using any of the vectors that are longer than necessary. So typically, there will be only one choice, although it may happen that if it falls exactly in the middle, that one would also be good. I can, of course, also take negatives, but that wouldn't change the flag. So that is also a reasonable condition. And then I also want that not only am I doing the best I can, but I'm actually doing well. I am improving the situation. I'm making the size smaller. So this is clearly a directed graph. That is why I'm talking about arcs rather than edges, which is what the graph theory experts tell me to do. So if we make such a step along an arc, then we make progress, and that progress is what I define to be the length of the arc. And that is just the quotient. How much is that one larger than that one? But since I like to think about these lengths as being additive, if I take two steps, I want the total length of those two steps to be the sum of the lengths of the individual steps. So for that reason, I don't take the quotient itself, but I take a logarithm. So that means that if you do a succession of steps in this graph, then the sum of the lengths of the arcs that you are stepping over is simply true is simply the logarithm of the size of the initial flag divided by the size of the final flag that you end up in. So these lengths give me a good idea of the progress I am making. Oh, I see that I have a little exercise here for people who like dual flags. Just a little footnote. The flag of the reduction graph of a lattice and that of its dual are entirely the same. So if you perform this sort of thing for a flag or for its dual, that makes no difference, which certainly inspires interesting questions. For example, whether you can find a member of your class of algorithms that has sort of a symmetric behavior, a self-dual behavior. And you can wonder how useful it is to, every now and then, replace your lattice by its dual. That suggests several questions that, to the best of my knowledge, are still open, but that I do not have time to go into. Okay, so here is a theorem, which is not a trivial theorem, sort of a tedious proof. It gives you a bound for the length of a path. So I see that this theorem could have been stated a little better, because this length, the length of a path here, is not intended to be the sum of the lengths of the arcs in it. No, it is just the number of arcs. Yeah, the sum of the lengths from f to f prime, that is exactly this logarithm as I explained. But the number of flags, or rather the number of steps that you are taking to get from f to f prime, according to this theorem, is not much larger than the gain that you make in the size. So the gain that you make in the size is measured by this logarithm, and then you add 1, otherwise the theorem is wrong, and you multiply it by a constant that depends on the rank. Now this is a theorem that I won't prove for you, but it gives you an idea of what one can prove about this reduction graph. But I have another very good reason not to prove it, apart from the fact that the proof is tedious. Namely, the theorem is not good enough for us, and we won't need it. But still, let me comment upon this magnitude. What I'm really interested in is, starting from my f, I want to have an upper bound for how many steps I'm going to make. And you see, this upper bound is only in terms of f prime where I end up. You may not know where you end up. But in all practical situations, you can give a lower bound for this as f prime. I told you already that there is a lower bound for the sizes of the flags of a given lattice, and for practical lattices, you can really write down such a lower bound. For example, if all inner products are integers, it is perfectly easy to show that the size is at least 1. In fact, it is, from its definition, it is a product of numbers, each of which has a square that is a positive integer. And if L is not having integer inner products, but rational inner products, well, then something similar is true after scaling. So this S of f prime, you should think of in this theorem and in similar ones as something for which you have a perfectly decent lower bound, so that in a theorem like this, you can simply omit it. And that means that you really should be happy with this theorem, because it gives you a logarithmic upper bound for the number of steps you're going to take. And that is what you want in a polynomial time algorithm. You want to have an upper bound for the number of steps that is at most a logarithm of your initial data, and, well, the size of a flag that really represents the size of your initial data. So one way of paraphrasing this theorem is that it tells you that if you start at any flag, then after not too many steps, after no more than a logarithmic number of steps, you find one that you like. That is to say that you like, if you fix n, because I am psychologically trying to make it look as if that b is constant, but I'm really admitting that it isn't, it depends on n. If you like your lattice basis reduction algorithms to have a good behavior also as a function of n, so if you don't fix the rank of a lattice, but if it gets very large, then it becomes vital to give an estimate for this Bn, an upper bound. And here is a theorem of that nature, and it's a rather bad one. It is an exponential upper bound for this B of n. And you see it is not polynomial at all. It is exponential in n. And that means that the upper bound that I gave will not suffice to prove that the class of algorithms is polynomial time when you really view the n as being part of the input. And if you would like it to be, then it would be sufficient or maybe even necessary to prove an upper bound for Bn that is no more than a constant power of n. That is an open problem which I recommend to your attention. So how do we get around this problem? Well, as I already tried to suggest, we are going to be a little bit more modest. We don't want to have this 4/3. That is not what we insist on. We take any number that is larger, like the 2 that I used by way of illustration. And then, if you use a larger constant, then it has the advantage that the SF over SF prime really has a lower bound bigger than 1, so that you have really a substantial step that you make. In the case that I replaced the 4/3 by 2, what did we get? We got a half plus a quarter is 3/4. Then you see that you reduce the size of a flag by a factor of at least the square root of 4/3. So that means that each of the steps in my path will have length at least the logarithm of the square root of 4/3. So that means that the number of steps that you take can be no more than the total logarithm divided by that lower bound. So how do I formalize this? Well, what I do is that I take a subgraph. I take some number L, which is going to be a lower bound for the lengths of the steps that I allow myself to make. And L may be small, but it should be positive. And I don't want to make small steps, because if I make small steps, I may make too many of them. So I keep the same vertices, but the arcs of small length I delete. Then it is perfectly clear, if each of the steps has length at least L, that the number of steps in a given path will be no more than the total length divided by this L. So that is, as soon as you fix L, a perfectly reasonable logarithmic upper bound for how many steps I need to make in my subgraph. And then you do a little worse. You won't achieve your 4/3, but as I argued, you will achieve something a little larger, depending on L. And if you work out the details, then it turns out that what you achieve is this function of L. L should be less than the logarithm of 2. It is clear that you cannot make your vectors more than twice as short in this two-dimensional picture that I drew in general. L should be less than the logarithm of 2. If you take L equals 0, which is not allowed, you get the 4/3. If L approaches log 2, then this C approaches infinity, and the thing becomes useless. So you just pick your favorite L. It is a parameter of your algorithm, but now when I fix L, I do get a polynomial time algorithm. So the conclusion of all of this is that if I take any constant that is greater than 4/3, you can figure out which L belongs to it from a little bit of arithmetic, then given this C, you have a polynomial time algorithm that produces a flag that is good with respect to that particular C, as long as your C is strictly larger than 4/3. So that is, according to what I say here, the LLL algorithm, but as I explained already, it is really a whole class of algorithms. Okay, so let me then spend the remaining amount of time indicating a few additional applications of the LLL algorithm. One is an algorithm that I already alluded to last time, and I will only sketch it in a rather qualitative manner. It is one of the original applications of the LLL algorithm, namely factoring polynomials in one variable over the integers. And I take my polynomial to be primitive because I don't want to get into the problem of factoring integers. So what do I do? Well, first of all, for technical reasons, I make my f square free. Once I have the irreducible factorization of f divided by the repeated factors, you can simply check how often each of them occurs in f. And the main reason to do that is in order to make the numerical analysis easier, namely, having this f, I want to find its complex roots. So then I take my numerical mathematics textbook and I find a complex root, it may be real, of f, and I approximate it so that it has rational, real, and imaginary parts. And this epsilon, how small you need to take it, well, that is what I'm not going to tell you about. You have to figure out epsilon sufficiently small so that the whole thing is going to work. Of course, what you need to do now also, if you want to prove anything about the performance of this algorithm, is show that these numerical algorithms can be done in deterministic polynomial time. So that is something else that you have to check the literature for, and that can be done. Then I take L to be, well, you might say the space of polynomials of degree less than n, where I identify a vector with a polynomial whose coefficients are the entries of that vector. But then the quadratic form that I use indicates that I am not interested in any integer vector, but I'm interested in integer vectors that have a good chance of vanishing in alpha, in the sense that if I plug in to the polynomial an approximation to alpha, which is beta, then it is going to be small, very small, and I make it small by giving that term, this absolute value square, a very large weight. So n and epsilon need to satisfy inequalities so that the whole thing works. And then what do? Well, you apply the LLL algorithm to this lattice, and you find a short vector, and what do you do with the vector? Well, you hope that that is going to be somehow an irreducible factor of f. And why is this the case? Well, suppose that f is reducible. If f is reducible, then this alpha will be a root of a polynomial of degree less than n, namely one of the irreducible factors of f. If that factor is 0 in alpha, then it will be very small in beta, because alpha and beta are small, and I can give a priori estimates for the coefficients of my irreducible factors. So then this will be very small, tiny, and this will be of a reasonable size, so this will be a vector. The coefficients of that polynomial will give me a vector that is much shorter than I would expect on the basis of, for example, Minkowski's theorem, which would be something like the nth root of the determinant which grows with this capital N. So you get a surprisingly short vector if the thing is reducible. So if you don't see a surprisingly short vector, then f must be irreducible. So if f is reducible, then this LLL will find a vector. Well, it may not be so incredibly short because I have to pay for this slight exponential factor, but that is still good enough. As it turns out, LLL will find a vector that is still quite short. And the converse is also true. If you find a vector that is quite short, then I claim that that vector gives me a polynomial vanishing in alpha. And why does it vanish in alpha? Well, just by going down the same chain of arguments in the opposite direction. If this is short, then clearly the last term must be small. Then taking the n out, this really must be tiny. Also, the x's are not too large, otherwise the thing wouldn't be small. If this is tiny and beta is close to alpha, then if I plug in alpha instead of beta, it will also be tiny. And yeah, algebraic numbers that are too tiny have to be 0. It is like integers that are less than 1 in absolute value have to be 0. So as soon as you know for an algebraic number an upper bound for its denominator, and you know an upper bound for the conjugates, then you will have a lower bound for its size just by using, for example, the fact that the norm of an algebraic integer that is non-zero is at least 1. So if it is too tiny to be compatible with all those other data that you can deduce, then it will have to be 0, and then you have identified a polynomial vanishing in alpha of degree less than the degree of f. So if you take a greatest common divisor, you will have found a non-trivial factor of f. And if you are a little bit careful about this, you can even guarantee that the non-trivial factor you are finding is irreducible. So the upshot is that all you do is you simply find LLL to find a short vector, the first basis vector in your flag, that gives you a polynomial. Compute the GCD with f. If g is 1, then f is irreducible. If g is not 1, in this description, I've been not so careful to be sure that g is irreducible, then you factor g and f over g recursively. So that is one of the versions of using LLL for the purpose of factoring polynomials. Let me also put up a sheet here which is closer to what is in the published literature and maybe also closer to what people do in practice. I have been talking about complex roots of f. It turns out to be easier to use a p-adic variant because p-adic numerical analysis is easier to provide with an efficiency analysis, especially when you can customize the choice of p to the polynomial f that you are looking at. It is important here, as you see, that the discriminant of f be non-zero. Okay, so that is just one of the additional applications. There are certainly more that I could talk about, but not within the time that has been allotted to me. I thank you for your attention.
Question. So if you're seeing bigger than the 4/3 and you don't see it in the graph, right?
Then, what is the question?
If you're seeing bigger than 4/3,
Yes.
and so you have an upper bound for the size and lower bound for the size, you don't get a graph. You use a graph.
Yeah, so
If each step drops the factor.
I'm not quite sure which question you're asking.
With each step you drop non-trivial factor. So
Yeah, so right. Every time you have a drop in the size of the flag, and since the size of a flag cannot be too small, the number of steps you can take is no more than about the logarithm of the initial thing. Say there's a lower bound 1 for the sizes of the flags. That is right. So this theorem that I wrote down with the B in there, as I mentioned when I put it up, we don't need it. Right. It's a hard theorem. Tedious. Not deep, but with a 4/3, right. Well, it is sort of interesting. Also, I proved it last year, I want to tell you.
Do you think there is an efficient way to find, for example, Minkowski reduced basis by taking C equal 4/3? I mean, there with some optimal reduced basis on L, is there any efficient way to find, for example, Minkowski reduced?
So Minkowski reduced basis, that is, what is the definition of that? Is that just one that every step you take the shortest one that you can do? Yeah, so that type of question is apparently very hard. If you fix a dimension, then you have polynomial time algorithms for accomplishing that sort of thing, which are essentially obtained by first running LLL to get the sort of an approximation, and then search an entire n-dimensional box for better possibilities. For larger n, I believe that people think that finding the shortest vector, the shortest non-zero vector of a given lattice is too difficult to do, NP hard maybe, or whatever the proper terminology is. But that is, I believe, not really proved, although people have random versions of that, or...
Finding the shortest vector is NP hard with respect to randomized reductions.
Right, with respect to randomized reductions, that is a careful restriction, an important thing to keep in mind. Of course, we don't want that. Other questions?
Let's thank the speaker again.